equations are we going to have here? It's 4 equations, 4 unknowns. Equation 1 will be, I'm going to write it down, it's the partial of v with respect to x equals lambda partial of g with respect to x, which for us would be what? What is the partial of v with respect to x? 8yz equals lambda times the partial of g with respect to x, which should just be 18x. All right. Our second equation is the partial of v with respect to y equals lambda times the partial of g with respect to y, which is 8xz this time, lambda, and then partial of g with respect to y is 72y. And then equation 3, partial of v with respect to z equals lambda partial of g with respect to z. Kind of getting the same thing happening here. 8xy, lambda, and then what, 8z? And our last equation is the actual constraint itself. All right, there we go. All right. Yeah, so this one, that's why I showed that to you, because I want you to see like this one. If I just hit this with x on both sides, y on both sides, z on both sides, they'll all be equal to one another, right? And I need to, if I'm going to do that, then I need to suppose that that all x, y, and z are not 0. But that's not really even something we need to consider. Because remember, we're trying to find the maximum volume of this box, right? And if x, y, and z were 0, the volume of this thing is 0. So that's not even in our minds as a possibility, right? So this, suppose x is equal to y is equal, I should not write it that way, that's bad. X is not 0, y is not 0, and z is not 0. So suppose that those are all not 0. Then my first equation, equation 1, becomes 8xyz equals, I'm going to kind of rearrange this, 18 lambda x squared. And then equation 2, y'all know what I'm doing? X, y, z, right? Okay, so then the second equation is xyz equals 72 lambda y squared. And equation 3 becomes 8xyz equals, 8 lambda z squared. All right. Okay, big deal. Now what? They're all equal to one another, right? So I can set them equal to one another. So I can set these two equal. How about I set these two equal first? So when I set those two equal, I get 18 lambda x squared must equal 72 lambda y squared. I'll move everything to one side. So I'm setting equation 1 and 2, right? Equal to one another. So I move everything to one side. 18 lambda x squared minus 72 lambda y squared must equal 0. I'm going to factor out, what, I can factor an 18 out, right? 18 times 4 is 72. So I can pull out 18 and I can pull out lambda. And I'll be left with x squared minus 4y squared equals 0. So that means that either lambda is 0, right? Or x squared minus 4y squared equals 0. Now, I'm not going to go through the work because I think we've gone through enough of these. I would have to do suppose lambda 0. Okay, lambda can't be 0 because if lambda is 0, that would force one of those to be 0. And if one of those is 0, then our volume is going to be 0. Right? Yep. Okay, so I'm just going to look at this. This implies that x squared must equal 4y squared, right? If that's equal to 0, then that's true, right? And I'm going to just stop there because I realize where I'm going with this. This right here is going to be plugged in here somewhere. And I'm going to leave them as squareds because it's squareds in my fourth equation. So that's what I get from the first one. That's kind of like this all right here is just setting the first two equations. Now I'm going to do, let me go ahead and write that down. This was equation 1 equals equation 2. Which two should I set together now?
Equation 2 and 3.
So if I do 2 and 3, I'm going to get a relationship between y and z, right? I'm going to do 1 and 3 because that'll give me a relationship between x and z, right? So I already have a relationship between x and y. If I had a relationship between x and z, then I could get rid of my y's and my z's and replace them with x's. So that's why I'm going to do 1 and 3 now. Equation 1 equal to equation 3. You could get it by doing 2 and 3, but I think you'd have another intermediate step in there. Or no, you could solve it for the y's instead of the x's, but either way, we're going to get there. Okay, equation 1 and 3, I've got 18 lambda x squared must equal 8 lambda z squared. And then we play the same game. We move everything to one side. 18 lambda x squared minus 8 lambda z squared equals 0. Here I can only pull out a 2 in a lambda. So I pull 2 lambda, left with 9x squared minus, pull out 2 there, so 4z squared. So again, lambda can't be 0 because it messes up our x or y or z. It messes them all up. So from this, I can conclude that 9x squared must equal 4z squared. Any questions? All right? Sure? All right, so now we're ready. We can go to equation 4. Equation 4. Let's see what equation 4 becomes. I'm going to leave this as 9x squared. Now, what would 36y squared be? And remember, here's my relationship between x and y and x and z. So 4y squared is x squared. So 36y squared would be, hit that one 9, hit that one 9, right? 9 here would be 36y squared. So this should be plus, what? 9x squared again. And then plus, what is 4z squared? Well, we happen to have it, don't we? 4z squared is exactly 9x squared. So this is another 9x squared, and all of that must equal 36. So this is 27x squared equals 36. And so x squared equals, we'll divide both sides by 27. We'll reduce the fraction. We should get 4/3. Okay. Y'all all right? Okay. So then what is x? X is either plus or minus 2 over root 3. But I'm only going to be considering the positive answer here because remember how we came up with this? We said we were in the first quadrant. We went out x, out y, and then up, right? So I'm only going to be looking at the positive answer here. So x is 2 over root 3. Okay. Can I get y from this? If I know that, right, then I can come here and get y, can't I? And if I know x here, I can get z. So I should be able to recover y and z now. Now before I do that, I'm just going to kind of take a step back. What were the things that we assumed here? Just that these couldn't be 0, right? Which we already know we throw out. We don't have to worry about that. That'll give us 0 volume. Lambda being 0, I had to consider, but again, it makes these be 0. So this is the only thing we have to look at. So this is either going to be a max or a min. But we know it's not a min, right? We know it's not a min because any other point that lives on this, would, if you compare it to this one, would be smaller. How do we know that? How do I know that? Look, here's an example. The point 200. Does that live here?
Yeah.
So 2 squared is 4. 9 times 4 is 36, right? 0, 0. So that point lives on this restriction, but it gives me a volume of 0. So that's definitely going to be smaller than what I get here. So all we really need to do now is recover the y and the z. So let's get our y now. So x is 2 over root 3. Y will be, so we can do it right here. I'll do this one. Y squared is 1/4 x squared. So I'm using that equation right there. And let's see, x squared is 4/3. So this is going to be y squared equals 1/4 times 4/3. So 1/3 is y squared. So y is equal to 1 over root 3. And again, I'm only going to look at the positive answer. Finally, we have to get z. So to get z, we know that from this, that z squared equals 9/4 x squared. That means z squared equals 9/4 times 4/3. And that means that z is equal to root 3. Okay. So have we answered the question? We have not. It says find the volume of the box, maximum volume, right? So what is the volume? Well, this is our volume function right here, right? So we've got to plug that in. So the volume at the point 2 over root 3, comma 1 over root 3, comma root 3 will be equal to 8 times 2 over root 3 times 1 over root 3 times root 3, which is 16 root 3 over 3, right? 16 root 3 over 3. That is the maximum volume that you can get out of a box inside that ellipsoid. Now, that may seem like it was quite a bit of work, but I guarantee you, had you gone the other route from the previous section, you would still be working on that. Probably from the beginning of class, you'd still be working on it, because it's a lot of work. All right. Done with that. We're not done with Lagrange, but we're done with that. Let's see if we can just set this one up. I want you to look at it, think about it for a few minutes. See if you can set this one up. What I mean is, can you give me...
Before you read it, is that...
Oh.
Isn't it 16 over root 3? Oh, okay, never mind. I see now. I thought it was,
You sure?
I thought it was,
Did you cancel one of the root 3's?
Oh, yeah, we canceled the root 3 over the root 3.
Let's see. It's the same thing, because when you rationalize, you get... This is where we were, right?
Yeah.
So one way you could do is you cancel those, right? You get 16 over root 3.
Yeah.
But then if you rationalize root 3 on top and bottom, you wind up here. They're the same answer.
I thought the square root of 3 was still on the bottom. And that's all.
Gotcha. All right, take a look at that one. See, so what we have here, and I should have mentioned this before, is that the f that we are working with in these problems, whether it be f of xy or f of xyz, this is called the objective function. And then the G equal to K, that's called your constraint equation. So in the previous example, our objective function was the volume function, and our constraint was the ellipsoid. On this problem, can you come up with the objective function and the constraint? Let's not go through all the work, but let's just see if we can set it up. So find the maximum volume of a rectangular box with double bottom if it is to be made from 81 square feet of cardboard. Two bottoms of the same size, so you're doubling it up, I guess, for reinforcement. So think of it like a cardboard box. You have 81 square feet of cardboard to work with. You've got to make this thing out of that 81 square feet, and you have to have a double bottom, and it does have to have a top, sides, front, double bottom, top. Can we come up with the maximum volume possible from that? So I think you should maybe draw a picture first, right, of a box. Do you want me to let you work on it, or you just want me to crank through it? Crank through it? Okay. Sounds so eager there. All right, so we have a box. And let's throw some arbitrary dimensions on this thing. Let's call this x, let's call that y, let's call that z, right? Why not? We want to find the maximum volume, right? So what would the volume of this box be? The volume is a function of three variables. It would be x times y times z, right? So this is our objective function. We want to know the biggest this can ever be. But we're not allowed to just like let x and y, z be whatever the hell they want, right? We have a constraint to x, y, and z. What is that constraint? The surface area of this thing has to be 81, right? So let's talk about the surface area of this. What would the surface area be? So what would the area of this front be? X times z. And then we've got a backside. That's terrible. That was terrible. That was absolutely terrible. Okay, so we have this backside, right? That's another xz. So I'm gonna say it this way. The surface area has to be 81, agreed? 81 must be the x times the z, but two of them. Plus, what about the side here? That side, y times z, but then you have another one, right? So two yz's. Okay, what are we missing? The top and the double bottom, right? So the top here would be, what would that top one be? X times y, but then on the bottom I have another xy, but twice. So how many xy's do I have? Three of them. There you go. So look, make this the biggest it can be, but you must stick to this equation. So there's your constraint, there's your objective function, and then you go to town with it. Make sense? Does this problem look somewhat familiar to you? No? Cal 1? So there's like a classic problem in Cal 1 where you're given like a thing of cardboard or something. And you're told, like, let's say this is like 12 feet, that's a big piece of cardboard, by 20 feet. And you're told you're supposed to like come in, cut the corners out, right? Yeah. And then you're supposed to fold up the corners and see like how you can make the maximum volume of this. So you imagine cutting this, folding up the sides, and creating this shape right here. And the thing about a problem like this is that when you do a problem like this in Cal 1, you can get everything down to one variable. everything can be one variable. So you don't have to worry about like any complexities because one variable, then you just use your techniques. Here, this is a lot harder because you got a lot of things at play here, right? You have 3 things. Your surface area, that surface area equation that we have, has 3 things controlling it. So it's not as easy. You might be able to get it down to 2, but with Lagrange, it doesn't matter. We can leave it at 3. So, okay. Let's see if there's anything else here. Another one where we can set this one up and not go through the work. Find the point or points on the sphere, blah, 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 closest and farthest from the point 3, 1, negative 1. Wow, okay. So you have a sphere sitting here somewhere, 3-dimensional space. You've got a point sitting here, 3-dimensional space. And you want to find the point or points on this sphere that are closest to that point and furthest away. So let's start with the idea of what we're trying to find the max and min of. Like a distance, right? So somewhere here, right? Well, you know, I want you to think through this one. I could just tell you, but I want you to think through it. What is our objective? What is the constraint?
The constraint would be the distance, the thing, specific, no, the
surface of the sphere.
The surface of the sphere? Does it make sense that would be the constraint? Then what's your objective function? Distance between what? The point and a certain point, right? So the way I think you should look at this, let me bring this point down so I can put it almost here at eye level with me. It's like you're sitting here at this point and you're saying, okay, look, there is a formula out there that will give me the distance from me to any point, okay? There is a formula, like if you give me some point, x, y, z, there is a distance to that point, right? So that is our objective function, some distance function. But I'm not allowed to just like look around anywhere, right? I can only be points here. That's our constraint, makes you force yourself to be looking at just the points that live there. So our distance function is going to be very arbitrary. Okay, our distance function, which I'll call d of x, y, z, is the distance between our point in any arbitrary point in 3-dimensional space. So what is that function? Square root, difference of the x coordinates squared, difference of the y coordinates squared, difference of the z coordinates squared, right? That's our standard distance function. Square root of the difference of the coordinates squared, sum of the squares of the difference of the coordinates. Yeah. So that's our objective. And then our constraint is that those points, those arbitrary points, can't be arbitrary. It's got to live on this. So this side will be your G, and this is like your F. Now, do you agree that the gradient of this is going to suck?
Yeah.
yes.
Okay, so there's also something in Cal 1 you should have learned, and that's anytime you're trying to optimize or maximize or minimize a distance, that it is equivalent to be able to maximizing or minimizing the square of the distance. Do y'all remember ever hearing that in Cal 1? So the way it works is this. Let's say that we determine that this point right here has the furthest distance. Call that D. That any other point out here, like if we go from here let's say to here, that this point right here, I'll call it P, I'm sorry, that distance is P, that P is smaller than D, all right? Then the square, okay, the square of this distance is still going to be bigger than the square of this distance. So what that allows you to do is, instead of looking at this, we look at something like capital D, which is the square of that, which is this. And so what we do is we go through the whole job of figuring out, doing Lagrange on this. Whatever x, y, and z we get, whatever answer works for this and makes this the max and min will also make that the max and min. And so you can use your answer, x, y, z, in this to get the actual distance. So it's much easier to take the gradient of that because you don't have the chain rule and all that to worry about with the square root. And that almost wraps up Lagrange. What if we have a function of 3 variables and 2 constraints? Okay, so remember the problem we had where we said, let's say that the function of 3 variables is the temperature in the room. And then I said, okay, imagine now you can only live on a sphere in the room and you're looking for the maximum temperature on that sphere, right? Well, what if instead you have a sphere with a plane cutting through it? Now that creates this like circular path on the sphere. So what would the max and min be on just that circular path? So it's not only the sphere, but the intersection of the sphere and the plane. So now you have 2 constraints, the sphere and then the plane. So can we do this? And the answer is yes, we can. But it gets ugly. It gets ugly. What happens is that instead of your gradients having to be parallel, we have this. We have these 2 new functions, right? We had the g, but now we're introducing this new one, h, a second constraint. And so what we need is that the gradient of our objective function is not just parallel to the gradient of g, it must also be, how do we say this? This vector must be some linear combination of some scalar times the gradient of g plus some new scalar mu times the gradient of h. And so what you wind up getting here is x, y, z, lambda, mu. 5 equations, 5 unknowns. And so your equations look like this. You have gradient of f, or sorry, partial of f with respect to x must be lambda partial of g with respect to x plus mu partial of h with respect to x. And then you have 2 more. And then you have the 2 constraint equations. And that gives you a total of 5. We are not going to do these, all right? We aren't going to do these. This is just to show you. I believe there's one problem in the homework that you're free to work through or just to skip. It's just, and the problem they give you is very, very easy. Like one of the gradients like turns out to be like 0, so it just basically turns into equation, 4 equations, 4 unknowns. The idea is more important that, look, that we can continue to extend this. You know, if we have a function of 3 variables, we can have a single constraint or 2 constraints. We have a function of 4 variables, we can have a single constraint, 2 constraints, 3 constraints. It all just depends, right? All right, we're going to put Lagrange to bed. I actually coded up my own stuff here at the end of this. I know none of y'all are using these notes, the interactive notes, but I was just doing the Lagrange can be a real pain in the butt. So I coded this up a few years ago where I can just put my objective function, I can put my constraint, I can put my constant, like constraint equal to constant, and then it'll spit out my my max and min points. Well, it'll spit out all the points, and then it'll evaluate the function, and it'll tell you. And I did that if you have two unknowns, or function of two variables with a single constraint, function of three variables with a single constraint, function of three variables with two constraints. Yeah, that's all I did.
You didn't do any more?
So,
Just experiment with it.
well, it was the code actually wasn't that bad for these. It looks worse. The answer looks worse. Making it look pretty is what probably was hard. I haven't looked at this in a long time. Let's see what it looks like. Where is it? Can't even find my... No. Hold on. I'm bothered by this. Screen environment working. There we go. There it is. Yeah, see? I mean, it's not a lot of code, just a little bit. Most of that's just trying to make it look nice. All right, we're done. Chapter 11 in the books. So chapter 12, right? We only have an hour left. Deep breath, right? Deep breath. We're halfway through. We're supposed to cover chapter 10, 11, 12, and 13 in this class, so we are halfway through. Chapter 11 that we just finished was called partial derivatives. That's what it was called. So if we go back and take a look at what we've done, we started out chapter 10, three-dimensional space, vectors, dot product, cross product, lines and plane equations, quadratic surfaces, vector functions and curves, arc lengths, curvature. Then we did functions of several variables, limits, partial derivatives, tangent planes, chain rule, directional derivatives, gradient, max and mins, Lagrange. So the end of chapter 11 was a lot. 11.7 and 11.8 are very heavy sections. But that's kind of like the crux of it all. Like we want to be able to find highest and lowest points on surfaces. Now what we do, all of that was derivatives, right? It's time to go the other way. So now chapter 12, multiple integrals. So we're going to do antiderivative time, all right? So we start off this discussion with the idea of a double integral. And we're going to take a little bit of time to just review, not much, but just a little bit to review what our standard integral is. So we have this notation that we use for definite integrals, right? Integral sign, we have this thing, this a and this b, right? That's our limits of integration. So essentially that integral says if we have some function f, we start it here at a, we end it here at b, and we want to know this area, then we have to find the antiderivative, right? And then evaluate that antiderivative at the two endpoints and subtract, and then we've got the area, right? And that's just awesome. Fundamental theorem of calculus, beautiful. It's amazing it all works out that way. But what's more important is the way we got to this formula and what this notation actually, where it came from. So the whole idea in Cal 1 is that you have this function, this curve, right? This blue curve, which is our f in this case. And we want to find the area under it, so we cut it up into all these rectangles. And in this case, you know, I've used the right endpoints. That's not important. But we want to get like a more accurate, we want to add up all those areas, right? And what we do to make it more accurate is we make the width of the rectangle smaller and smaller and smaller and smaller, and then our error starts to go away. All right? So in the setup of this, sorry it's so grainy looking, our domain was an interval on a number line. It was everything between a and b, right? When we talked about finding the area, the Riemann sum, we would take just one arbitrary rectangle and we say to ourselves, what's the area of just that one rectangle? And we say, okay, well, it's the height of the function, f of x, at some point in here, and then times the width of the function there, which is delta x, but later on becomes dx. So essentially, the area of one of these is just the height times the width. So it's this times this. I mean, I'm very loosely putting this together. It's a review. And then what we did is we said we want to add them all up, right? We want to let these go and become infinitesimally thin, and we want to add up all infinitely many of them. And so this summation, this is a finite sum, the sum of all of the rectangles, height times width. When we let this n go to infinity, this becomes this. And so this integral sign is actually, the idea behind the integral sign is adding up an infinite number of things. And then the integrand, this part right here, was height times width. That's all I want you to take away from this. Because understanding the elements of this integral is going to make it much easier as we progress in this chapter and the next. Height, width. All right, now, our goal now is to take a surface in three-dimensional space, sitting above the xy plane, and imagine casting almost like a shadow down on the ground of this surface, and then trying to figure out what the volume below that is. Instead of area, now volume, right? So how would we approach doing this? Well, the same way we did it in Cal 1. We take our surface, and below it, we start filling it up the space with boxes, right? So we have our actual surface. Let me see if it comes in here. No. There's our actual surface. And what we're doing is we're trying to fill it up underneath it with these boxes and find the volume of each of those boxes. And the more boxes we have, the more accurate we're going to be, right? So I could have, let's say, let me refine my boxes, make them a little bit smaller, more narrow, right? And then I'm going to get a more accurate measurement. And then I can go even more. And that's going to give me even less error. And if I could somehow put an infinite number of boxes underneath the surface, I would actually get this, wouldn't I? So the idea is the same as it was in Cal 1. It's just the actual construction of this is going to be a little bit different. But visually, it's kind of the same idea. It's just we're extending to three-dimensional space. Let me back this up because that'll slow my computer down. All right, so how are we going to do this? Well, our domain now is on the ground, right? It's not a number line anymore. It's not everything between A and B. It's some shadow of our surface down on the ground. So our domain is here, everything in blue. What we want to do is we want to take this little piece of this domain and make a little box out of it, where the width of it is delta x, just like it was in Cal 1. But now we have a little height to our rectangle, which is going to be dy, or change in y. And then from that, we want to pick a point in here, plug it into the function, and that'll give us a height for our box. So we have like a length, and then a width, and then a height of the box. And so the volume of that is this times this times this, which is that. And then we want to add them all up, right? But the thing is, we have to add twice. It's like we have to go back to this picture. It's like we have to add along one direction first, holding one of our variables constant. So we add this way, and then we want to add the other way. And that's why we need a double summation. So we have a sum and then another sum that moves us in both directions. And so our integral, when we take the limit of this and let these things get infinitesimally small, we get this double integral. Okay, integral, integral, and then we have the volume function right there. Height, length times width. All right? Does that kind of make sense visually or no? It's arbitrary because as this thing shrinks, the point becomes irrelevant. And the same thing happened with Riemann sums. I don't know, did you have to do Riemann sums by hand? Did you have to do like right endpoint, left endpoint, midpoint, trapezoidal, all that crap? If you did all that, then you realize later that at the end of the day, when you take the limit, it doesn't matter, because that thing's becoming infinitesimally small, so your point's getting squashed down to essentially a single point. And that same thing happens here, because this right here is a box, you're picking an arbitrary point, but as it shrinks infinitesimally, that point can only go to one place. Make sense? Okay. All right, so this is our definition we're going to start working with. It says that the volume between a surface, a function of two variables, the volume between a surface and the xy plane, which is z equals 0, over the rectangle R, which we will write closed interval AB crossed with closed interval CD. Don't look at that as a cross product. These aren't vectors. That's just a notation. Is given by the double integral. So we write double integral over R. R is our domain of the function of two variables, f of x, y, dA. So this is new. dA stands for that infinitesimal little area on the floor. Okay? So this is our little patch, a little square on the floor. So this is really our height, and this is the area of the base of our box. Now that area is made up of multiplying dx and dy. Now notice the order of things here, because it's important. When you look at this, let me make it a little bit bigger. When you look at this, we are going to be talking about an inner integral and an outer integral. So this right here is the inner integral. So you're going to do this integral from C to D of our surface with respect to y. So when you take the antiderivative here, you have to do it with respect to y. And these limits of integration are your restrictions on y. And then after you do that, you're going to get this answer, and then you're going to do another integral, but this time with respect to x, and then use your restrictions on x. Now you can also flip it around, do it the other way. So you can go and do your inner integral is with respect to x first, restrictions a and b, figure out that answer, and then do it with respect to y. So the order in which you do it does not matter so long as you are integrating over a rectangle. So I'll illustrate this in an example, all right? Sometimes just doing an example is what we need. Okay. So let's find the volume under this surface on the domain 0, 2 cross 0, 2. So I'd like for us to just draw the domain real quick. The domain of this is everything in here. So all these points in here are being plugged into the surface, and then we're looking at the volume of that thing straight down onto the ground, right? So our x's here are between 0 and 2, and it turns out in this problem our y's are between 0 and 2. So do we all agree that this is a rectangle? If we have a rectangle down here in our domain, then the order in which you do the integration does not matter, all right? So now here comes the volume of this. The volume will be the double integral over R of our surface with respect to area. Okay, so instead of saying with respect to x, I'm going to say with respect to area. Now specifically for this problem, I'm going to go A to B, then C to D, and then I'm going to do our function, and then I'm going to choose to do it with respect to y, then x. So again, pay attention to the fact that my inner integral has y, so my restrictions here have to be my y restrictions, C and D. This is A and B. So what are my limits of integration on my outer integral? That's 0, 2, right? I should have used like 0, 3 and 0, 2 for this example, just so you could distinguish the two, but these are restrictions on x. Then the inner integral, because it's with respect to y, is going to be our restrictions on y, which is also 0, 2. And then what is my surface that I'm integrating? 16 minus x squared minus 2y squared. Okay, I'm going to put that in parentheses. Now I'm going to be integrating that with respect to y first, then with respect to x. So that's the actual, like, written out, ready to go. Let's do some integration. And we're going to start with this first one. And we're taking the antiderivative with respect to y, which means we're going to treat x like a constant, okay? And we're doing anti, not derivative, right? Antiderivative. So let's do it. I like to do it this way. I still leave the outer integral here, and then I put a bracket and I figure out everything I need to figure out. So what is the antiderivative of this with respect to y? So antiderivative of 16 with respect to y is 16y, so I'm going to put 16y. And then what is the antiderivative of negative x squared with respect to y? Negative x squared y or yx squared, right? Same thing. So since we're treating x like a constant, because we're integrating with respect to y, this is all a constant. The antiderivative of a constant is the constant times the integration variable, so negative x squared y. All right? And now this one, minus 2y squared, the antiderivative of that with respect to y, well, that's just our standard power rule for antiderivatives. So what is that? Negative 2/3 y cubed. Now that's our antiderivative. We need to evaluate it, right? So we have that evaluation bar that we usually use. And on the top we would put 2 and on the bottom 0, yes? Now because we are now going into multivariable integration, I'm going to add something to this. I'm going to put y equals 2 and y equals 0. And that's because as we get to triple integrals, you need to know like which one's being replaced. Like are you replacing the z or the x or the y? What's being replaced? And in this case, we're replacing the y's with 2 and the y's with 0, right? Not the x's. So I'm going to add that little element. And then after all that's done, once I figure out what all that is, I need to do another antiderivative with respect to x. So let's do this evaluation. So this equals, all right, I'm still going to write the integral sign. 0 to 2. All right. So I know on the next step I plug 2 in and then I plug 0 in, right, for y, and then subtract the 2. So I've kind of set it up for myself to do that. Let's go 2 in for y. So we've got 32 minus x squared times 2, so 2x squared. So 32 minus 2x squared. And then what's our last term?
That's going to end up being
16/3. Minus 16/3?
Yes.
Okay. And then we plug 0 in for y. And that's actually pretty pleasant, isn't it? Yeah, because that's just 0. All right. So maybe I don't need all that room. Okay, integral 0 to 2. And do y'all want to combine these? These are both constants. Do y'all want to combine those? We just multiply 32 by 3. So that'd be what, like 96 over 3, and then subtract 16. So what's it, 80/3?
Yeah, 80/3.
So I'm going to be doing 80/3 minus 2x squared. That's what I get, right? After I get that first integral done, and then I'm going to integrate that with respect to x. And so we go again. So this will be no more integral because I'm taking the antiderivative. Antiderivative of 80/3 is going to be 80/3 x. And then minus 2/3 x cubed. We're evaluating this at x equals 2 and x equals 0. So 2 is the only one that really comes into play here, right? The 0 is going to kill everything off. So 2 in for x, what's that, 1/63? And then minus, let's see, 2 into here, 8/16. So we get, at the end of it all, 144/3. And then whatever that is, you can put that as a decimal, but that's the volume of that solid. And we don't have any units, right? Like units were not given to us, so this could be like cubic feet, cubic miles, cubic inches, whatever, but we're not given that here, so. All right, pretty straightforward. Integrating, doing double integrals over rectangles is like the easiest way to do double integrals. It's when it's not a rectangle is when it becomes a problem, which is where we're going, but we've got to start somewhere, right? So look at this one. Okay, so find the, oh, I didn't show you what we just did. Sorry. I didn't actually show you a visual of what we just did. So we said we had that rectangle on the ground, right? We said we had some surface sitting up here above it. And we said, all right, what we're going to do is we're just going to imagine just those points in there getting mapped into the surface, which gives us that little piece up on top. And then we wanted the volume of everything below that. So we found the volume of that piece in there to be 144/3. Okay? What about this one? Why don't you try setting that one up? Just write out the double integral first, then we're going to go around and see what people have. I'll give you like another minute to just write it out. Don't try integrating yet. Okay, who wants to share with me their double integral, their limits of integration and everything else? Go ahead, what do you got? First, the outer integral, what are your limits of integration on this one?
2 to 1.
2 to 1?
Mm-hmm.
Okay, so like that. And on the next one?
Pi to 0.
Okay, like that.
Then you have the equation y sine x times xy
Okay, and then
dy dx.
dy dx. Okay, good. Did anyone else do it differently? You flipped it? Okay, so if you flip it, you go this way. But this has to be flipped also, right? So dx dy. Now, we haven't gone into depth about this, but these should give us the same answer. I haven't formally said that or given you a theorem or anything yet, but they should. Is there a preferred way to go on this? Or, you know?
The first one?
I did the second one.
So think about this. If you had to integrate this with respect to y first, then x is a constant, right? Right? So I'm just going to kind of throw it in here. Like if you were asked to do that, what technique of integration would be required? Integration by parts. You'd have to do it by parts. to do that integration, because your variable y is here and in here. Right? Now it's actually x, so I don't want to leave that there, right? So this is going to require integration by parts on the first integration. But if you switch the order here, now y is your constant. And so this may as well look like this, 4 sine of 4x. And could you integrate that with respect to x? Without any technique of integration other than just like you know what the antiderivative of sine of something is? So this would actually be preferred if I was working through this because the integration's easier. Do you all agree? So that is something you want to pay attention to. Order of integration, sometimes one way is better than the other. So I'm going to choose to do this one. So let's find our antiderivative. I'm real curious to see how we do with this. What is the antiderivative of y sine xy with respect to x? So negative cosine of xy is the antiderivative. Right? Because the derivative of cosine of something is negative sine. So negative negative would give you the positive. So we know to take derivative of that, we're going to get the positive sign. And then we have to take derivative of what's inside with respect to x, which would just be y. So the y would pop out. Yeah. No? Go ahead. Ask.
Why would it be negative y cosine x1?
Negative.
Times,
Negative. Negative.
or isn't that y just the no.
The y is a constant here, right?
Yes.
Okay, so here's what I'd like. Let's do it this way. Let me do this. Let me do this. Sine of 4x. What's the antiderivative of sine of 4x?
Negative 4.
Negative cosine of 4x, but you also need to multiply this times 1/4. Because when you take the derivative of what's inside, you're going to get 4, right? So you're going to have to scale it by 1/4 to kill it off. So when we do, if I just do the antiderivative of just that, I'm going to get negative cosine of xy times 1/y. But I already have a y out here, so yeah. All right, so that's it. And then we're going to be replacing x, right? X with 0 and x with 2, right? And then once we're done with that, we'll do our integration with respect to y.
It's 1 and 2.
Was it 1 and 2?
Yes.
What did I, yeah, 1. 1 here and 2. So now we plug in, right? We go 2 goes in for x, 1 goes in for x. Let's do that. Equals integral 0 to pi. And I'll have two things that are going to wind up being subtracted here. And I'll do that with respect to y. So when we plug in 2 for x, we get negative cosine of 2y. And then when we plug in 1, we get negative cosine of y, like that. We just replaced x with 2 and x with 1. And before I integrate, I'll go ahead and clean it up. This is going to be, this is minus cosine 2y, and this becomes plus cosine y, right? So I'm just going to go cosine y minus cosine 2y dy, like that. And now we get to do antiderivatives again. So the antiderivative cosine of y is sine of y. And the antiderivative of cosine of 2y should be half of sine of 2y. Y'all still with me or not? Yeah? Okay. And then we're going to be doing this, evaluating from y equals 0 to y equals pi. Uh-oh. Sine of pi is 0. Cosine of, or sorry, sine of pi is 0. Sine of 2 pi is 0. Sine of 0 is 0. Sine of 0 is 0.